In this unit, we're going to combine the ideas of the derivative and the idea of a plane in two variable functions to introduce the idea of a tangent plane, which will combine those two. We're also going to move on later on to functions of multiple variables, their linear approximations, which is equivalent to a tangent plane, as we'll see, and how those ideas of tangent planes can be applied. First off, we'll start off with tangent planes, though. And the idea here, geometrically, I think is fairly intuitive. If you have a surface, say a nice smooth, simple surface like this upside-down parabolic bowl, then if we pick a point on that surface, we can define a plane, nice linear function here in two variables, that is tangent, that just touches the curved surface here at the single point, or that shares the slopes. If I look at the slope of the surface really zoomed in at that point, I would see something that looks like this tangent plane. And here it's just blown up for effect so we can see the contrast between the curved surface and the tangent plane itself. But there's something about shared slopes between these two objects at the point that we selected. So the important thing to remember here is that we have a surface defined, and then this is a point that's selected. And we build the tangent plane at a specific point. Let's see how that works its way out in terms of formulas. So if we have our two pieces here, we've got our function. So this is our curved surface, non-linear most likely. We're trying to compare that to a formula for z that defines a tangent plane. And we know a few ingredients. Like I just said in the picture, we want our tangent plane and our surface to share slopes. So we just have to compare how we get slopes for each one of these functions. The slope of our function in the direction of x is going to be df dx at ab, or sometimes we could write it, if we preferred, f sub x at ab, but in any case, the x derivative at that point. If we look at the tangent plane, what's the slope in the x direction? Well, if we just zip down our function here, we see here's the x term, and m is going to equal the x slope of the tangent plane. And it turns out we don't need this point specifically because a plane has the same slopes everywhere. That m value gives us the x slope no matter what x and y are. So if we're trying to build a tangent plane, so a plane that matches the function we've got, so we've got our function, we have got the point, what should we pick for the values for m and n in the tangent plane formula? Well, we want the tangent plane formula, or more importantly, the tangent plane slopes. To equal the surface's slopes at the point AB. Now how would we make that? Well, we would do that by setting m equal to f sub x at AB, the x slope, and n, which is the slope in the y direction, because it's the coefficient of the y term, to be the y derivative at AB. And last but not least, we figured out a, that's given, that's given. That's set as the f sub x, that's set as the f sub y, x and y slopes. The only thing remaining is the height. Well, we want to go through, we want a plane that goes through the point A, B. What's the height at that point? Well, the height's given by our function. That's our z value. And so c is going to be the value we get when we plug our x and y coordinates into the function. So at the point where xy is equal to ab. And that pretty much completes our formula. And you'll notice it's very, very similar to the single variable formula that we had before. So just a quick reminder here. In one variable, we had L of x, our linear approximation or tangent line formula, was equal to f prime of a, x minus a plus f of a. All we've done here is replace all the f's with f of a b's. We have another slope, and then we've added a term for the y direction, including a slope in the y direction. So that's how we extend our one variable function approach, where we find a linear approximation or a tangent line to a single variable function. Here's how we extend it to two variables. Here's a nice summary of all that. So here's our basic formula. The function at the point, x derivative times x minus a, y derivative times y minus b. And again, noting that these are values, the slopes are calculated at a specific point. So we get a number for these traditionally. Another way we can write this is that our curved function, the actual curved surface, is approximated by the tangent plane formula. And we can make use of that if it's helpful in a particular application. We'll see that as we go through some of the examples. All right. Sometimes it's also helpful to look at an alternative form. To get this form here, notice what we had. We had f of xy is approximately equal to f of ab plus all this other stuff. If we bring this over, what we do is make a negative sign there, and it's approximately equal to all this. This is the change in f. It's a difference between f between the f of xy, or the z value on the surface, on the original surface, and f of ab, which is the z value at the point of the tangent plane. So what we're finding, or what we can find, is, well, how does f change somewhere else in the surface? Well, it's going to be approximately the x slope times the step we take away from the point we've selected in x. We're also going to move away in y, and how does that change our height of the function? Well, we multiply it by the y slope, or the rate of change of z, or f, with respect to y. So lots of similarities to the single variable functions that we looked at before, and more importantly, I think for people who like memorizing formulas, this formula and this formula are identical. The only difference is how we present it. X minus a, that's a change in x. Y minus b, that's a change in y. We bring this f over, we get a change in f. So there's not two formulas here for linear approximations or tangent planes. It's the same formula, simply rearranged for convenience of thought or application. All right, let's take a look at an example to hopefully make this more concrete. What is the equation of the tangent plane to the graph of the function, some crazy combination of x and y, at some particular point? Now, you'll notice that we've given an x and a y, and this point here, we didn't need to be given that, but it's handy to double check that f of 1, 2 is 3 times 1 times e to the 2 over 2, which is 3e. Check. So this last value had to be the z value, or the output of our function. Otherwise, it wouldn't make any sense. And it just happened to be given here as a shortcut. You'll see examples in the homework where sometimes this z is given, sometimes it's not. All right, so let's just write down our general formula here for the tangent plane. And that is z equals the function value plus the x slope times x minus a plus the y slope times y minus b. So what do we have here? Actually, better yet, let's call this a and b. They're the specific x and y coordinates that we want to build the tangent plane at. So we've got ab, we've got f of ab. What are we missing? So check, got that, got that, got that. What are we missing? We're missing the x and y slopes. So here's where we bring out our partial derivative calculations from the last unit. If f of xy is equal to 3x e to the y over 2, That tells us that the x derivative of that, well, x is the only variable. We differentiate it, we get 1. We treat this as a constant, we leave the y in it though. And our y slope is going to be a little more complicated, not much. Y is the only variable, that means we're multiplying by the constant 3x, and the derivative of e to the anything is e to the anything times the derivative of the exponent, in this case here 1/2 if y is our variable. What else do we need? Well, we need this at the point 1, 2, which is our a and b points. And let's get our x in here, subscript. This is the general formula for the x slope at any point. Here's the x slope at the particular point we want. It'll be 3e to the 2 over 2, or 3e. And f sub y will be 3 times 1 times e to the 2 over 2 times 1/2. That'll be 3/2 times e. All right, so with that, we have fx sub ab and f sub y at ab. And so our tangent plane at the point 1, 2 for xy is z equals, what have we got? F of ab, that's 3e over here. We've got the x derivative, another 3e, x minus a, where was a? A is up here, a is 1. And last but not least, the y slope times e, y minus b, which is y minus 2. So that whole collection there defines our tangent plane to this complicated surface. Not quite sure what this would look like at first glance, but we can certainly go through a mechanical process and get the formula for the tangent plane. Now, one of the things we can do with that tangent plane is use it to approximate values nearby. So notice we're asked to approximate f of 1, or sorry, approximate f of 0.95, which is close to 1, and 2.03 for y, which is close to 2. Well, handily enough, that approximation we just built should do a fairly good job on that. Let's try it out. So from the tangent plane, from our tangent plane we have z is equal to, we had 3e plus 3e, and now our x is the 0.95 minus 1 plus 3/2 e, and our y value is 2.03 minus 2. There we go. So after some calculator work, we get the value that this is 7.869, and we believe that this is approximately f of 0.9. Notice this is the approximation. This z value is on the tangent plane. This is moving a little bit away on the tangent plane, and we're interested in comparing that with the surface value, just for reassurance here more than anything else. We have the surface, and we're going to try to compare the z value we get from the surface. And let's just finish this off. 0.95, 2.03. And if we do the same calculation from the surface, f of 0.95, 2.03, that's going to equal 3 times 0.95 times e to the 2.03 over 2. A little more complicated calculation here. Certainly not one we could do by hand, so we'll pull out our calculator. 2.03. And that is equal to, again, we're approximating here, we're rounding off, 7.864. Hey, that's pretty close. So we note the similarity here between these two values. Similarity. So these two values are very close to one another because the values we selected here, 0.95, was very close to the center of our tangent plane approximation, and the value we selected here was also very close to the tangent plane point. And so we expect that there's not much divergence yet between the plane and the surface, whatever it happens to look like. One last feature of this example I'd like to bring out is how explicitly we see the delta x here. The point that we did the approximation at was x equals 1. The point we're trying to estimate the x at is 0.95. And naturally, as part of this combination, we take the difference between those two things. Likewise, in this term, we have a delta y. So we see that other relationship that I talked about earlier, that other form of the tangent plane approximation in the calculations here very obviously. So this is actually something I look for when I'm going through these problems, is just make sure, oh yeah, do I have a difference between where I started and where I am right now? If I don't, then I should be suspicious. So that's just something to keep in mind as you go through these kinds of problems. Let's do a second example here then, just to reinforce the ideas. We've got our function, and we're interested now in finding the points in the graph where the tangent plane is parallel to the xy plane, where it's horizontal. And hopefully, if we sketch this out a little bit, imagine your surface. There's going to be some points, some magical points, where the tangent plane is completely horizontal. That's what we're looking for here. That's good. Other points that we might find would have tangent planes that would be off on some sideline, and we're not looking for that. So the question is, how can we look for those using the tools that we've built up so far? Well, clearly we're going to need the derivatives, and for that, I think it would be helpful to rewrite our function as a power. It'll make the derivative easier to calculate. And eventually I'll complete the entire function before putting my brackets in. There we go. To the negative 1. Again, doing this simply because it makes the differentiation process easier. All right, so what are we looking for? Find the points in the graph where the tangent plane is parallel to the xy plane. So we could do this two ways. We could build the tangent plane formula, or we could recognize what we want, which is in the tangent plane to have z equals f of ab, that's fine, plus f sub x of ab, x minus a, plus f sub y at ab, y minus b. Well, if we want the slope of the tangent plane, or the shape of the tangent plane, to be perfectly horizontal, then we'd better have both of these slopes equal to 0. That's the only way we're going to get a tangent plane that's perfectly horizontal. And if that's the case, well, we don't have to go through all this calculation. We can just focus on those two slopes. And so we set our goal. Find AB such that both, and this is important, such that both f sub x at AB and f sub y of AB equals 0 at the same time. That will mean our x slope and y slope on our tangent planes are both 0, or that the tangent plane as a whole is going to be completely horizontal. All right, if that made sense, then what we need to do is get to our derivatives. So from our function here, so 1 tells us that by differentiation, we can get the x derivative, and that'll be all of that stuff to the negative 2, and negative, bring the power down front, subtract 1 from the power, times the derivative of the inside, which will be 2x minus 2. Also, the y derivative, notice the derivative of anything to the negative 1, if it has a y in it at all, will be the same thing, negative times the whole thing, times the y derivative of the inside, no y, 0. So those are all 0 derivatives, and then 2y as the last point. All right, let's just do this on the next page for clarity here. So we have f sub x, I'm going to rewrite this, minus 2x minus 2 all over, sorry, negative times the whole thing, negative 2x times 2 plus x squared minus 2x plus y squared all squared, and f sub y minus 2y over 2 plus x squared minus 2x plus y squared all squared. There we go. And what are we doing with these? We're setting both of these equal to 0. Okay. Why are we setting them equal to 0? Because we want the points where the derivatives are both going to equal 0. And the nice thing about that is, if we're setting things equal to 0, the denominator does not play a role. The denominator does not play a role. And so we have simply negative 2x minus 2 equals 0. Bring the negative over. 2x equals 2. X equals 1. And we also need that minus 2y equals 0 or y equals 0. Now here you have to go through a little bit of logical checking. Have we got both cases? Is it any point that x equals 1 or points that x equals 1 and y equals 0? Well, if we just look at these two formulas here, to have both f sub x equals 0 and f sub y equals 0, the only way to make the x derivative 0 is to have x equals 1. And that only gets me half of what I need. I need both of these equal to 0. So I need to get fy equal to 0 as well then. And so we must have both of these true. And what that tells us is only the point 1, 0 will have a horizontal tangent plane, or will produce a horizontal tangent plane on the particular surface, which was f of xy equals 1 over 2 plus x squared minus 2x plus y squared. Original function, and the location where we're going to get slopes of exactly 0. There's only going to be one single point where that happens, so whatever we know about the surface, typical axes here, x, y, z, only the point 1, 0, I don't know quite what the surface looks like, but that is a single point at which the tangent plane, if we built one, would be perfectly horizontal. In fact, I think I got ahead of myself there. Let's sketch what that might look like. Here it is in a bit more detail. X, Y, Z. So we're at the point 1, 0. Whatever the surface looks like, that location has a horizontal tangent plane. There we go. So that's another insight into where we're heading, in fact, because if you notice this sketch anyway, that point where the horizontal or the tangent plane is horizontal also happens to be a local maximum of the function, because there's no higher point. Any other direction I go, I would go down afterwards. So we're seeing some inklings of where we're going to head in terms of optimization of multivariable functions as we move through the rest of the units in the course. For now, it's enough to see how we would identify this point using our ideas of the tangent plane.